Another draft physics video presentation. So a couple of comments and then we'll move on to something like photons, I think. But anyway, lensing maybe. Just, yeah, something like that. Anyway, so this is regarding the dissidents in the physics community, where they actually now and then point out how something isn't really proven, and then in the same breath almost they'll do the same thing, which is promote some idea that's completely unproven or undemonstrated by any hard evidence, real evidence, and call that some sort of sacred scientific process where you just make crap up, and and the standard isn't that it actually explains a phenomenon, it's just that it fixes some other notion that you want to keep alive. So I don't know if there's parallels, but I mean you can sort of see it in this battle between religion and science on subjects like evolution, where there's all this desperate where the missing link evidence, the focus on one fossil, and so much is built out of it because both sides are desperate to validate their theories, and so they emphasize any tiny irregularity, any tiny not exactly consistent with the rest of the field of information. Well, anyway, and you can just see the same thing going on where there's just this kind of silly desperation, and obviously as evolution has become more and more established, the desperation on the side of the dissidents is more obvious. But anyway, funny how she dresses like Star Trek character and signed off with the Vulcan thing. Yeah, so I did notice the Vulcan thing also, but yeah, I didn't think of the Star Trek character, but yeah, she does wear kind of modern clothes. I guess, I don't know. Yeah, totally not religious thinking going on here. Yeah, I don't know. She seems a pretty focused, not too frivolous. But then again, hard to say. Cult of the Invisible Man is a perfect analogy. Well, I don't know if it's perfect, but it's clearly the analogy. You could just say gremlins, too. You could say any kind of pixie kind of theory. Physics is pixelated. They actually think there's little pixies controlling the universe. But anyway, she attempts to question science which they put forth, yet tries to ride the fence because of the power and money that is against her. So you're thinking she has some sincere doubt about the validity of these made-up concepts of dark matter and dark energy and the whole bent space bullshit and all that. And I don't think she has any, frankly, but she wouldn't defend them. And so this idea that everybody is intrinsically dishonest, and all these scientists are just fundamentally dishonest people, and they go out and bother to make a video being dishonest on purpose to show how they're really with the cause. And I don't buy that in the first place. So I think that's just a conspiracy theory and blah blah blah. So nonsense. She can easily be destroyed, as so many people have been. So can you show me this evidence of the so many people that have been destroyed by the physics establishment that weren't like religious kooks, pretending to be physicists, and they're constantly trying to turn physics into a religion or something overtly, and that maybe a laboratory would fire them because they really weren't doing science anymore, they're just looking for God or some kind of bullshit like that. But can you give me a list? Is there some sort of name list somewhere of all the people who have had their life ruined because they went against the establishment? Just be curious to see this list of so many who have been destroyed. So I don't buy it. Yeah. Of what I speak, I am sure. No, I really don't. I mean, obviously there's an obligation, if you want to be part of their club, to do their club stuff. But I think they're actually really are indoctrinated. I mean, they don't just they're not mouthing the words like the Pledge of Allegiance in school or something. They're not just sitting there going, I don't want to do this, and I don't want to say that, and I don't want to be a part of this. This is stupid. I'm not one nation under God and all that bullshit. Fuck you with that shit. Just let's just have a be nice pledge. We don't need all this fucking propaganda in the pledge. Be a nice person. Yeah. Okay. There. Now we're done, right? So again, so your conspiracy theory is that there's a bunch of these poor, they can't realize they have no freedom to speak their mind. I just don't think they have any mind to speak. They're so indoctrinated into this nonsensical mathematical horseshit as the answer, that they just don't see any further than that. They think the real universe is some sort of formula, and in the explicit sense, not in the yes, you can formalize the relationships between things. Heavy things are always heavier than lighter things. There's relationships that exist, and they define rules about how things will behave. And but I think there's so much. Look at how much freedom they have to make up bullshit. So you can hardly say that they're restricted when they make up many worlds interpretation, Copenhagen, the other nutty random everywhere theory. They have a whole bunch of different theories. So clearly there's no obligation to read the pledge. It's just none of them seem to be interested in physics being physics, physical. So there's no new Einstein out there defending or attempting to defend the fact that there's got to be something fundamental in physics. That there's underlying principles that we haven't seen yet. And they're just not looking, frankly. Well, whatever, you're entitled to your opinion, but I don't, it just sounds like rubbish. A lot of dissidents are outcast for damn good reason, because they are just nutters talking shit, frankly. So Zohar, nice guy and all, but, I don't know. I've been over this already, but anyway. I'd love to have another talk interview with you soon. Well, you have my Skype. You can message me on Skype, It does work. Just type message. No problem. But every time I try to send you an email, I get an email telling me my email to you didn't send. Yes, well, you're sending it to the wrong address. I have more than one email address. I already pointed out that I had to move the domain name, okay, because GoDaddy got way too expensive. So I moved the draft physics domain name to another registrar, and it was half the price. But the unfortunate fact is it doesn't forward the email unless I have a hosting account, and so I'll move it to another different account in which I do have a hosting account, but I just won't get around to that tomorrow. And so you can't send to draftphysics.com. Right there in the bottom of the description it says ds@donotgo.com. That'll get to me. Gary and Mendham will get to me. Lots of things will still get to me, okay? But you can't use draftphysics.com and send an email to me. You have to use something else. And then on both the websites, there's an email forum. That mail gets to me. So, I'm sorry, but shit. I've already been over this. So anyway, I already said these exact words in a video. I don't know how you missed it. To you, pointing out that you can't use draftphysics.com. Shit. Please let me know if there's another way for me to reach you. Skype. Yes, there's lots of other ways. Anyway. Alright. I don't know if we even need this thing up here now. There really isn't. People are just, well, whatever. Nobody's making any interesting videos. It's just so disappointing. Anyway. So, thinking on photons. one thing I thought about against the whole lensing argument, another point to make, all right, is that we have this illusion. See, our eyeball doesn't look at the universe like stuff comes in straight into our eye and we see stuff exactly as it is. Instead, we're seeing stuff based on a fact that our eye looks at the universe this way. So objects close and far away look like they get smaller, but they really don't. Okay, they don't change size because they change size relative to our retina. So the size of the object in our retina changes proportional to perspective. So the further away an object is, even though it's the same size, say the real size is this size, right? The real size is this size. It's always the same size, but the percentage of our perspective it takes up, okay, our point of view, our perspective, changes, and that's what makes it look smaller. It didn't get smaller because it's further away. It's just that we have distorted it by putting it in a bigger frame. We have this in a really big frame when it's far away, and it's a little tiny frame when it's close up. And that's really the only thing that makes it look smaller. So if you think about what light has to accomplish to get to us from distant objects, you have to remember that the thing so let's say there's a galaxy out here somewhere. The galaxy could be 100,000 light years across. I mean, just humongous. So it's a gigantic thing. But it's very far away. So, yes, when we look at it, we're doing this perspective thing. Our perspective keeps getting wider and wider. And so we make that big thing look very small. But it's still a big, giant thing. And the light that gets to us, now even though, I mean, obviously if I have something this size and I look at it from here, these angles are going to be pretty sharp. And the further away I put the object from where I'm looking, the more parallel the lines can get. But they get more parallel. They don't get parallel, okay? They're still far from parallel. And for half their trip, they're pretty far away. So for us to realistically see a galaxy billions of light years away, you have to believe that somehow these photons, okay, ones that are hundreds of light years, thousands of light years, distant from each other. Photon from over here and a photon from over here, very, very distant from each other. And they both have to make this voyage all the way to this tiny little point for us to see them. And so you'd have to believe that the gravity on this photon, that's traveling this path, and the photon this path, that they're somehow going to travel through a piece of space, with all these other little blobs flying, being in the way, all this other crap, that somehow they're going to have exactly the same gravitational effect. So as they're going through space, they're going through this obstacle course of junk. Yeah, you can see that, right? There's all kinds of junk. There's no way you can draw a line, through any part of the universe, so to speak, but there's no way for you to draw a line, a path, where you won't have an unevenness in the gravitational effect. Even if you have the same exact mass on this side as you have in this side, they have exactly the same amount of mass. The fact is you will go closer to different objects, and so you won't be able to be affected by the same amount of gravity on one side to the other, or forward and up and down. There'll always be a difference because you're just going to happen to be closer to some galaxy here, and you'll get much more gravitational effect just by an accident of proximity, because you can't make a line where the whole path has exactly the same gravity. So there's no path through space where there's the same amount of gravity on both sides. So you have very little likelihood that the photon from this, even if you were sending photons straight, parallel, you would have very little likelihood of having the same amount of gravitational effect on one side as you did the other. But the fact is, these are starting from way far away, so even by half the voyage, this thing is still half the size it's still 50,000 light years of separation between the photons. They're still really far apart in space. And there's absolutely no reason to think this one got affected, this photon got affected by the same amount of gravity as this photon. There's no, it doesn't make any practical sense. There's no way you would get a clear image because in a sense the disproportion of the gravity would be doing plenty of essentially scattering of the photons, moving them a disproportionate amount and screwing any chance of you collecting a consistent image from the location, because so few of the photons would be able to make the journey without being sent to the wrong location. And so even if you could see the image should be horribly distorted because you get to see this you'd see this photon in this location and you'd see this photon over here, and the whole thing would be messed up. There's no way you could actually see these spiral arms and all these details, because all the details would get ruined by the fact that the photons are coming from very different paths through the universe, and those different paths are inevitably going to have very different gravitational tugs on them. So I don't think there's any practical answer to this problem, that there's no hope that you'd get a clear image, if you got an image at all. So it kind of points out another reason not to believe light is bent by gravity. It's just not a good theory. There's not good evidence for that theory. And again, it's just typed as one of the proofs of Einstein, and it's in fact one of the proofs against at least that portion of Einstein. Now again, I wish I could say that if I prove that Einstein was wrong about photons being bent twice as much by gravity, so that's even the funnier part. They're supposed to be bent twice as much by gravity. So there's even more expectation that they'd be influenced badly by having to travel billions of light years through space without being distorted, profoundly distorted. All right. But yeah, you still can't kill relativity even if you just killed the photon thing, because the photon thing really was a throw-out line by Einstein doing this stupid equivalence principle, a principle he shouldn't even have bothered with, because all acceleration is not exactly the same. Being affected by gravity, having gravity go through and hit every one of your atoms is very different than somebody, you standing in a rocket, and the rocket taking off and the force having to go through your feet first and then get to the rest of you. They're just different ways of acquiring velocity. Alright, so the principle of the photon, again, let's go through it. So they have some notion that a photon is, I don't even know how even, some wave thing. Okay, some wave. They understand that it's polarized, so they understand sort of that it has this set out of alignment, or width of the wave, height of the wave, but the wave is still some sort of straight thing, except when they want it to be something else. I don't need, it's like I say, you can't describe it because they want to make photons go everywhere all the time, and it, obviously the single photon can't be doing that. It has a polarization. It's going one way, and I would argue that this is as a composite, this works. It's understanding that but if you really want to understand the photon, what is it? Well, the photon really is chunks of energy that fall in this pattern. That the little bits are on these lines, and they can be separated by these distances. And so the photon is just frequency, a set difference between the distance between them, and they go this way, the speed of light, and you can distort them by putting them through different obstacles. So you can affect these positions and the frequency. So if I put it through a polarizer, or I send it through space, either one, it's going to encounter small atoms. So understand the atom. I drew these as little round things, but obviously these are just points of energy. They can be infinitely small. Well, they can be very small, infinitesimally small, something like very small. And this distance is many atoms worth. So these things are really, this is smaller than an electron. Obviously 2,000 atoms, I can't draw 2,000 atoms, but atoms, it's 2,000 atoms worth of distance between how much alignment these are out of, which would be, actually millions of electrons worth of distance, and photons are even smaller than the electrons. So the odds of this hitting the same electron would make no sense at all. I mean, there's just no realistic hope that this spread out thing is going to hit one electron in one place and do a specific thing. So photons do rely on the fact that there's more of this stuff. The photons are on top of each other. There's a whole bunch of different photons, different and they can be a little bit out of alignment. Like I could make another photon that was just here, right? The little bits were this far apart, and I'm halfway between, let's just say. So I can just put them in this, so this is also a photon because it has the right separation between each blue bit. And so it's at the right frequency, it's in the right size container, it hasn't gone too far out, and it's going to hit a piece of matter, and this can be interpreted by the matter. The atoms have a relationship to each other, a crystal of some kind, let's say, and any impacts on them will be recorded collectively and produce the same impact on the other side to produce a new photon, you could argue. But it can react to either all of these little bits. Even though I made this one blue, I just made it blue so you could see that it's at a different phase than the other photon. But they all have the same exact amount of energy, and all this thing knows is what is it getting hit by, what pattern is arriving on the surface, and how can it rebuild, refind the pattern. And that's all that matters, is you're hitting it with a pattern. So instead of it just being chaos of a bunch of things just hitting without any, set pattern, it's got a pattern in it, and the pattern can be recognized by the atoms. So unfortunately there's no way to keep drawings in perspective, because the perspective gets so small. So then when you're cutting this down to what is probably happening on the smaller scale of atoms and the electron, and the idea is that one of those little bits will hit an electron, and it will affect it in a certain way, move it. And then if the electron doesn't get hit by another bit, so it's moved further away from its proton, you could sort of argue. The implication would be that if you hit it, you move it farther away from the proton. And and so if you hit it again before it moves back, right, it's going to want to move back. If you hit it again before it moves back, that is, another little bit hits it here, then this electron will move much further out, and that, you could argue, is going to impinge on another atom, which will cause its electron to bounce out. So if one electron goes far enough out, it forces this electron to go out, and that's what we call electricity, you could argue, or the migration of the effect. So it doesn't have any effect if just one little bit hits. It just gets absorbed and wasted, essentially, right? It just causes this little movement, and it just moves back. But the moving back and the moving does cause pressure that moves through things, so I can't say for sure. This might be the end effect rather than the, I guess the point is that causing the electrical thing is different than just causing the transmission of the movement itself. But you could argue that once this moved out here, that this electron would also move the same space, and then that's going to cause the next electron to move the same space because all the electrons are in balance. So you got to understand that when the regular universe is sitting here at any one moment, every single particle, every single little bit is seeking parity. So there has to be a parity between its attraction to the proton and its repulsion to all the other electrons. And there has to be, for every single electron, that has to be there's a balance. That's what it's seeking. It's seeking the balance place. So if it's not balanced, it's moving, and to find balance because it's being pushed by something. And so when you're sending photons into something, you're obviously going to, whatever balance there is, you're obviously going to unbalance it to some extent. And because everything is balanced to the position of everything else, this electron, every single one of them is not, they're not tied to each other with a rope, anything physical. They're tied to each other by pressure. And so once you change this thing's location, you change the pressure on every other one, and they're all going to be moved in some way or other. And really what you're just saying, photons have to somehow coherently transmit the movement caused by the impacts of the little bits of the photon. It has to transmit that through in some consistent manner to be called transparent. And if it's not transparent, it means that the pressure is being spread in different directions, and it just ends up being heat. Or the photon can reflect and not go through the objects at all, in the sense that the electron just does some kind of U-turn on the surface. The electron moves in and then moves back out again, and so it's just sending the energy back to the universe. So it went in and went back out, and before anything else hit it, and so therefore it just reflected the photon. Alright, that's probably, so I mean, just in theory, this model of a photon works. It's mechanical. It fits the evidence. And so I guess we'll just go the step further, which is how do you mess up photons, and then how do you reconstruct them? So there is no destructive interference. There's just reconstructive photon. You can just remake them again. So the idea would be is if you have a slit or some other material, the little bits are going to go into the material, and you can just see that this little bit might get killed. So now this photon has lost one of the lines of its wave is broken, because it got wiped out. So you can understand that, okay, well, there's other photons going through, and maybe some other photon will have some other bit knocked off, but it'll still have this bit, this one in the right line. And so you can just put the one piece from the other photon with that one, and how much, you could have 10 in this position and 5 in this position and 7 and 3. And so whatever the lowest number is would be the number of the photons you have. So even though you have, there's a bunch more going through, we don't see every photon from every position. You're seeing a whole bunch of different photons. You're not seeing the same photons going to some other location. And they're really just how much stuff is at these locations, hitting something in phase and, in the same positions, and that's a photon, So, and the other thing that happens is these little bits get flung off because they are going through electrons on this surface, and so they get put into different paths that they take. And when they take all these different paths, and also these paths, for example, this path, so they're deflecting in all kinds of ways because they're hitting electrons here, and the electrons are scattering them. So they're scattering coming off these two surfaces. And then you're just basically reconstructing photons because there's ones that are been knocked out of phase by that process because the distance, this line is longer than this line, and if it's longer by a wavelength, this right distance, then this broken piece and this broken piece can combine at a location and create a new complete photon. So one piece had this, this, and this, and the other piece had this and this. And if you add those two up, you get a photon. And so that's all that's happening is you reconstruct photons. There's no destructive interference. There's just breaking photons by having some sort of impediment. Now, in the case of the photographic polarizer, polarizing films, the breaking is quite obviously quite different. You're not just breaking pieces off, and you're not like I said, even the diffraction gradient is a bunch of little holes, and the little holes have electrons, and it's the electrons that are scattering. So they're the ones diffracting the light, spreading it, and by spreading it, they create the opportunity to take pieces from two different locations and reconstruct a photon. But in the case of polarizing film, it's creating another path length difference sort of thing, just because the polarizing film basically has two places where there's two layers of film and places where there's only one layer of film. So when the light's going through, some of the little bits hit the 2x one, and that means their phase will be shifted twice. So they'll go from being, in the position argument, they'll go from this position to this position. So now might be 2 bits there because this bit was essentially moved, to this location because it went through the 2x filter, and the rest of that photon went through the hole, let's say, and so it only got 1x shift. So that is the phase, everything just moved one step back, and so the photon is here instead of here. Okay. So it's just a phase shift. So all you're doing is messing with the phase. Now, obviously, if you mess with the phase, again, some photons are, the holes here are smaller than or close to the polarization of the photon. So you can understand if I'm trying to push something this size through this size hole, I have a high likelihood that sometimes it's going to go through there, sometimes it's going to go through this. I can have a high likelihood I'm going to break pieces off when I do this. That some pieces are going to go through the 2x part, and some pieces go through the 1x part. So a lot of photons, there's very few photons will go straight through, without, or hit the 2x filter, or just hit the 1x filter. Very few photons will do that. Most of the photons will have some piece of them go through the 2x filter and some piece of them go through the 1x filter, and therefore they're all going to be messed up like they're all going to have this problem where they have 2 bits at one location and then no bit. And yeah, you can see that. And so the frequency is broken. So there's going to be a lot of these ones with broken frequencies coming through, and the idea is that you can put another filter in this way, at a 45-degree angle, and you'll be able to reconstruct some of those pieces, because some of the ones you broke, you'll now fix them again because you'll give this one a phase shift and put this piece here, and now you have the right frequency and the right amount of the frequency. It's always the right ray length. You have to have a certain minimum number of those bits to make a photon. So a photon is a composite object. There's no such thing as it's a photon. Really isn't anywhere close to the truth. The photon is a ray, and it's a ray made of elements, and the elements are polarized in the sense that they're out of perfect alignment, and their frequency is just their distance from each other in space, and they all travel the same speed, and they all have, there's no such thing as this is a red photon. The little bits have no color. The only thing that has color is the frequency. All right, so that's probably enough of that. So yeah, I'm trying to learn, trying to figure out the simulation stuff. The one guy, Daniel in Australia. If anybody knows any Daniels in Australia, yeah, this whole coronavirus thing happened and he disappeared, and so I'm just wondering if something happened to him. Kind of disturbing. So anyway, so working on the other simulation thing, and yeah, I just don't know enough programming to be much help. But anyway, but yes, we should be there soon. It's you know, it's just a little nuisance stuff. So anyway, so maybe I'll do a simulation video just to go through some of what has been learned in the process of figuring how you balance forces. But anyway, yeah, so enough of a video. Until the next time and such. Lots of distractions lately. Anyway, yeah, that's probably enough.